And welcome back to System Software. So we are at the end of our systems programming section of the course. Bit of a crash course in systems programming. I know it's probably unfamiliar for probably most of you. I have not done systems programming. But hopefully as you've done the MyLS project, which is due this Thursday, you've got a little bit of a feel for how this system call stuff works. Reminder that this is due on Thursday. I'm starting to get more questions on EdSTEM about it. So does anyone have any quick questions besides, if you have specific advice for your program, come to office hours this week. Otherwise, do you have...
Can we use the C-type library?
The which?
C-type library.
For what?
Can we use it?
What does it do?
Like all the string functions and everything?
Yeah. You can use the string. So I think I have a comment here. So I assume you know how to do, malloc and string concat and stuff.
Okay.
Yeah.
Do we email?
What's that?
Do we email?
The project. So look here under submitting your project. There's very specific instructions about using Git to submit the project.
Do we have to malloc something to the project?
Oh, I thought you said email it. Sorry.
No.
Do you have to malloc something?
We weren't told about that.
I can't remember for this project. I don't think so. I'm sort of assuming you know how to do C programming. You could use malloc. I'm trying to remember if I did. You may not have to. You may be able to use automatic local variables to do that. But I'm just assuming you know how to use malloc already. Yeah.
So, you have to put most of your analysis, or is it provide somewhere?
The code for what? Well, I gave you example code in this using files for how to use the various system calls. So if you look at this project, these are the system calls you'll need to use in order to finish this project. So if you're not using all of these, you're missing something, or you're using some other library that is not directly calling these system calls or library calls. I gave examples on using all of these system calls in the using files lecture notes in the lecture. You can watch the lecture again. And the subsequent lecture, I even went over a little bit more. And there's example code here. So for instance, using p-error, here's an example. Here's an example of using open, read, and close. Here's an example of using the dir directory entry system calls. Here's using stat. And so my expectation is that you'll be able to write your own C program, cobble together the algorithm for MyLS for printing out these 5 pieces of information per file and looping over the directory. But to help you do that, I've given you examples to show you how to use these system calls. So you'll do it from scratch, but you have examples to show how to use each system call. So I try to employ this, and I'll show this today when I go over the next project, which is more complicated. But try to use this kind of when I talked about the tortoise and the hare. Try to use this approach where you don't write code right away. Instead, you write out your algorithm, the kind of granular steps, the coarse-grained steps of your algorithm, and then take each piece one at a time. So don't try to write this whole program at once. Instead, all right, how do I do this, number one? How do I get the names of each? So for instance, where do the names of the files come from? Which system call? Does anyone know which system call to get the names of files from? Yeah.
I was about to say readdir.
Say again?
Readdir?
Right, yeah, readdir. So if you look at the using files lecture, I go over this code here for printing out all the files and file names in a directory. So you have an example of using these system calls. And so for number one, you want to start with pseudocode or start with comments to say, all right, I need to loop over all the files in the directory. I need to print out the name. And so, and then when you go to implement it, look at the reference material. Look at what I gave in lectures, look at the lecture notes, look at the man page, and then start planning what you need to do. And only when you have a good sense of what calls to make, then start writing code, and then start testing it. Don't move on yet. Start testing the code, make sure it does what you expect. And then go on to the next one. So what system call do you need to find the number of hard links? Stat. It says it right there. So in the notes, there's an example of using the stat system call. So this isn't the exact code you need in the exact arrangement, but it gives an example of how to use it. And so you can incorporate that into your code. Does that answer your question? All right, other kind of general questions on MyLS? Yeah.
So we can always the only requires like one file plus the next MyLS file plus the next file plus like what we trying to get. Like it's only case that we can always rip it out, but there's one file, right?
As long as this self-check works, you're free to break up your program however you like. You can certainly do a single file and one make file that has a single target to build your program. But this is the beauty of using version control and build automation, is that you can architect or implement the code however you like. As long as I can clone it and build it, I and anyone else can use your code. And this is true in general of open source software. The reason that you can just go to GitHub, download and build, more or less, is because of this automation. And so that's why I have you do that automation, so that you can architect things however you feel comfortable. You can name things however you like, as long as we can run the code like this name of the code, we can build it, and we can clone it. And this, if you go into professional software development, this is the exact workflow that basically everyone uses, whether it's closed source or open source. This is the workflow. This is the the fundamentals of the workflow. All right, other questions?
Would we know if it fails with private test cases? Like what?
You won't know. Yeah, you won't know until you get graded.
Well, after could we know so we can fix it? Or?
Yeah, so I think just come to office hours if you aren't sure. We'll come to office hours and I'll go over it. Otherwise, I don't know. I think it'd be unfair to give out the private test case afterwards, because the people who submitted early didn't get that advantage. But we can go over it in class. They'll be similar to the public ones, which will be released. But if you're testing on your own, when I talked about in the first day of class, if you're testing on your own and following these directions, then you should be fine. The test case shouldn't have any kind of tricks in them. I'm not going to test like detailed error cases and things like this. But as long as you're following these directions, and if there's a misunderstanding of the directions or I'm unclear, then of course you're not going to be penalized. I won't penalize you for that. Some people asked about why their binary file was not being printed out. So why is it that? Why is that the case? Did anyone figure out why you might have gotten weird stuff? Yeah.
Well, the PNG file, so basically it's showing the ASCII data from the PNG file. That makes sense.
Yeah, this is. So some people were getting non-ASCII characters. So here in the instructions, I say any non-printable or non-ASCII characters. So non-ASCII characters are those outside the ASCII range. I think I showed this in class. So if you go say man ASCII, it'll show you all the codes for each letter of the alphabet. The non-printable characters are the characters that aren't associated with the symbol. Instead, they're like the new line character, tab, space. These are non-printable characters. Yeah.
Is there a function in something?
There may be. Okay, yeah, you can use C-type. I just checked the range when I wrote it, but yeah, there are functions that are like, what is it? Like is alpha, yeah, C-type. So there are some helper functions you're free to use. That's what you're asking about C-type, right? I thought you're asking about like string counting stuff. Yeah, you can use this stuff if you want, if it helps you. So it's like is print, but you can literally just check the range here. All right, so that's MyLS. If you haven't started this, please work on it, because they're debugging this kind of system call stuff is a little intricate. It's tricky to do, even though the algorithm may be pretty straightforward. So make sure you're working on this soon. There is a generous late policy, but make sure you submit something by Thursday. Otherwise, we don't accept resubmissions. Just to make sure you're actually starting on the projects. Okay, so that's MyLS. All right, so let's get back into system calls. So last time we left off with pipes. And if you recall, so first of all, what is a pipe? What's a pipe in the kind of Unix kernel world? Yeah.
It allows for the output of one call to be fed into
Yeah, that's exactly right. So that's what it allows for. And the way it works is you ask the kernel to give you a new pipe, and it's a pair of file descriptors. It's kind of like a special file where the kernel will take any data you write into the pipe, to the right end of the pipe, and store it for you or buffer it for you in the technical jargon of the kernel. And with the other file descriptor, the read end, any process that reads that file will get the data that was written to it. And by having this mechanism, you can communicate between processes. Processes are isolated. Processes think that they're the only program running on the machine because the kernel provides this idealization or virtualization of memory and the processor. And I also went over how this same concept is used for network programming. So when you're connecting your browser or your app, whatever it's doing, to some server and getting some picture or whatever, these are literally two processes, two Unix-style processes most likely, depending on what device, for pretty much all devices and most servers. These are Unix-style devices. These are Unix-style processes that are reading and writing files, special files. And that file is a socket, which is like a pipe that works over different computers, different machines. So how do we create a pipe in the Unix world? Okay, so in Bash, you use the pipe symbol. What's the system call that's used to ask the kernel to create a pipe? Yeah. Pipe. It's the pipe system call, yeah. So the pipe system call gives you two file descriptors. You pass it. So in C, outputs are not always through the return value. You can have outputs through the parameters as well. So you pass it a pointer to an array, and the pipe command will populate that array with two function descriptors, or two file descriptors. Those are the in and out of the pipe. And so the idea is, if you have two running processes already, and you've created a pipe, you can redirect one of the running processes standard out to the right end of the pipe, and you can redirect the standard in of the other process to the read end of the pipe. Does that concept make sense? Questions on that? Okay, so let's go over how we're going to set this up in our implementation of a shell program. So just as a reminder, we're going to the project that starting today, although it was up, I already kind of introduced it to you. You're going to be writing a command line shell processor where you'll implement, let me show an example of a pipe here. You'll implement a command line processor that will be able to run, for instance, three processes at once and pipe the input, redirect the input and output of those processes to each other. So you'll actually implement a kind of mini version of Bash, a mini version of a shell. And to actually implement this, you'll do all the forking and execing and piping to set all this up. Now, in principle, it's pretty simple to kind of put in a diagram, but using the low-level system calls, you'll have to kind of carefully do error management and set everything up properly. Yeah.
How does the pipe system call know what exact processes it's taking in?
So the pipe system call doesn't know. The pipe system call doesn't actually know. So let me go over the kind of what I called if you have a Bash process, the process that's kind of controlling this whole procedure. So this is a little review from last time. So what Bash will do is it creates the pipe, but the pipe is just two file descriptors. There's nothing about, it's just, and those file descriptors are open in which process are, so if Bash creates the pipe, which process has the open file descriptors? Yeah. And it's the parent process, so whoever calls pipe. So if Bash is the parent process, and you haven't created any other processes, when you create new open files or file descriptors, those belong to the process that called them. So just like when you open a file, your program, your program as a running process has those open files in its process descriptor table. That's file descriptor table. So you'll create this pipe, and then in order to set up the two processes, you need to. So how do you create processes in Unix world? Fork. And does that? So if I fork a new process, am I running a different program at that point? No. Why?
It just copies.
Exactly. All fork does is literally duplicate all of the metadata about your process, including its memory layout, whatever is in memory, which includes the running program. So how do we change the running program of an existing process? Exec, right, that's what exec does. So together, fork and exec create a new running program from a parent process. So if you have this bash process or this master process, the parent process, create a pipe, and now your parent process has these two new files that you can read and write to. But in order to redirect data between two other processes, we need to create those processes. So we create one process that we'll use for, so say we're doing piping ls to WC, word count. We'll fork a new process, and then we'll redirect its standard out to the pipe. And then run exec to get the ls program running. After we do that, we're going to set up the WC program. We're going to fork a new process, replace its standard in with the read end of the pipe, and then run exec to actually start running the WC program. Let me diagram what this looks like. Oops. Why did this happen? Okay. So here's this algorithm for doing this. So your shell will be called my shell, so that'll be the parent process of everything that runs. So who runs the my shell process? Who forks that process? Yeah, well, who's the parent of my shell?
Us,
What's that?
the programmer.
Well, are you a process? Are you a running program? I mean, maybe metaphorically, yeah. Exactly, yeah, bash. Well, so yeah, if you're running it from bash, which you will be for doing this test, but exactly right. So you run bash, and then when you run a program, bash is the parent of that program that you run. So up here somewhere is the bash process, and when you tell bash to run mysh, it forks and execs mysh for you. Because remember, you can't create a new process without forking from an existing process. And where does the initial parent process come from, or where does it get created? What's that? Well, that's the standard output, but the initial process. Init, yeah, well, it's the init process by convention. That might be implemented in different ways, but when the system boots, the boot process creates a new process for you. It starts with one program that you give the kernel to say, this is my initial program, and then from there, that's the ultimate ancestor of all processes. Okay, so we have our mysh program running. And so looking at this algorithm, the first thing we do is we call pipe to create a new pair of file descriptors for the read end and write end of the pipe. And which process do those file descriptors belong to? Which end? Who's the parent? mysh. Yeah, the mysh now has two new files that it can read and write to. Then we want to set up the fork, the process for running myls or ls. And is this ls yet? Is this the ls program yet? No, it's just a copy of mysh. Yeah, question. Fork creates a new process by duplicating the existing process. So now technically we have another process that's also running mysh at this point. So how did we do something different to make sure, if you're running the same program, it should be running the same program. How do we write a program that does something different in the child from the parent? Yeah.
Switch statement.
And what do we put in the switch statement? What do we test?
If the fork returns 0, then we're in the child process. Otherwise, it returns the
Exactly, yeah. So the return value of fork is the only difference between these two processes, and that's what the kernel sets up for you. So at this point, we're just running a duplicate of my.sh. And so we'll check that we're in the child. And so does this process have the pipe file descriptors or not?
No.
It inherits everything.
It duplicates everything, yeah. Yeah, it duplicates everything, including all open files. So this also has access to the pipe file descriptors because it duplicates everything in the process, including its open files. And that's the trick. That's why we can do this redirection before we start running ls. Yeah?
The duplication shouldn't have its own pipe when you're going like empty pipe, so wouldn't there be two pipes?
Well, so file descriptors reflect open files, not the contents of the file. So for instance, if I had opened like hello.c, you wouldn't expect creating a new process to make a new copy of that file, right? It's just creating a new file descriptor that points to the open file. See the difference? So that's the open file versus the file itself, kind of like the process versus the program. So file descriptors are open files, and when you copy them or when you make a new process, you're not duplicating the files. You're just making a new pointer to the open file. And the open file is, again, another table in the kernel that it manages. So this is just a pointer, effectively a pointer to the file. And this pipe file it's not on disk because files don't have to be backed by storage. File is an abstraction. It's managed by the kernel. So in memory in the kernel somewhere, there's a buffer to store the contents of this pipe. Okay, so this copy of my.sh has access to the pipe. Yeah.
What would happen if for some reason you didn't forward and it was still in the parent? What would you do then?
Well, we will still be in the parent because the parent process is also still running.
So like what if it doesn't return the child process?
Oh, well, there will be an error code. So that's why you need to do error checking. So if fork fails, then you check the return value of fork. If it's -1, it's an error.
What if it's not -1 or 0?
Then you're in the parent. Then so this is guaranteed by the kernel. This is the kernel's guarantee. So if you just look at the return value for fork, child process is 0, non-zero is the process ID of the child, and failure is -1. So all possible cases, at least that the kernel defines. So it should never return less than -1, for instance, as long as you trust the kernel is written correctly. Okay, so we've got our new process. It has access to all the open files, including the pipe. And so what we do in order to make sure that ls will go to the pipe instead of whatever standard out is. So at this point, if I've forked from bash originally, what is standard out, as long as I don't do anything else when running it, what is standard in and standard out for my.sh? Yeah. The terminal. Why? Why is it the terminal? Because bash is standard out and standard in were the terminal. And so what happens so standard in and standard out, those are open files. What happens to open files when you fork? Or what happens to the open files when you fork? They get duplicated. So if bash is standard in and standard out were the terminal, when it forked your program, it will inherit that standard in and standard out. So it's not that standard in and standard out are always the terminal. It's that they're always duplicated from the parent. That's why it's standard in and standard out are the same. That's why when you run a program in bash, it'll print to the terminal without doing any redirection. Okay, good. So what is standard out and standard in for this copy of my.sh? Terminal. Why?
Because it duplicated everything.
Duplicated everything from my.sh, and why did my.sh have the terminal? Because it duplicated from bash. Good, yeah, okay.
The original my.sh was called with a redirection to a file. Would the child my.sh also redirect to that file?
Yes, that's right. So that's a good question. So if you call bash with redirection, like you redirect to a file, what bash does is actually what we're going to see right now. It uses dupe in order to overwrite the standard I/O of my.sh before executing it. And so actually, if you can wrap your head around how this pipe process works, you'll understand how redirection works at the kernel level as bash does it. Because when we redirect to a file, it's kind of a simpler version of piping. You're just piping to an open file instead of to a pipe file, which will get read by another process. So that's exactly right. So bash has standard I/O as the terminal, but in its implementation, when it sees that you've given this little arrow, it will use dupe. It'll open a new file, and it'll use dupe to redirect the standard out of my.sh before executing it. So let's actually see how that works. Here, we can see how this redirection works in this in your my.sh program. So we have fork here. Standard out and standard in are duplicates of my.sh. So however you've run my.sh in the first place, that will be the standard in and standard out. All right. So does everyone remember how to redirect or change standard in and standard out? So that's the bash syntax for it. So the system call to do it, yeah, back there. What's that? Dupe or dupe 2. So yeah, somebody asked about dupe 2 last night. I went over had to read the manual again. They're all very similar. It's just that dupe with nothing so it's dupe is was the original system call, I guess. Dupe 2 is the 2 parameter version. Dupe 3 is the 3 parameter version. That's why I think it's called dupe 2, dupe 3. Dupe 1 will just use whatever new file descriptor is available. So file descriptors are just from 0, literally a table, a base 0 table of open files. Standard in, out, and error are the first 3 file descriptors of every process, 0, 1, and 2. So if you want to use dupe, you would first, and you want to redirect standard I/O, you would close one of those file descriptors, thereby freeing it for a new open file. And dupe will just take whatever file descriptor you have and just copy it to whatever open file descriptor you have. Dupe 2 will do the closing for you. It will overwrite. It's an easier way to do it, and I think it doesn't have race conditions either, but an easier way to overwrite or redirect an existing open file. Yeah?
So for these two, you have to supply it with the old file descriptor and then with that old file descriptor? So new file descriptor is the target that you want to close and modify. So it's kind of confusing. I'll go through the actual code of this, but it's kind of confusing depending on what you think is old and new. So old is like the one you have open already, and new is the file descriptor that you want to copy into. So you'll see when I get into the code, but old will be the pipe file descriptor, and new will be standard I/O, standard in, or standard out. But I'll show the code. Yeah.
This might be a dumb question, but like a file descriptor is basically like something that points to like the start of the file. Is that what it is?
So it just points. So the process just has a list of open files that you've called open. So whenever you call open, the kernel it maintains a table of all the files you have open. Open will add a new entry to that table, and it'll have what kind of file it is. It'll have where in the file you are. So if there's on disk, you can seek the different positions. It'll actually keep track of the current position. So you can use like read, because read is not idempotent, I guess is the word. Every time you call read, it actually moves the pointer into the file to a different location. But it's just a list of open files and information about what those open files are, and other internal kernel stuff like caching and things like this. Okay, so before we get into the actual code, let's see how dupe works kind of conceptually. So right now, my standard out, I think it's file descriptor 0, is the terminal. And so when we call dupe, what we're going to do is we're going to call dupe on the right end of the pipe, and we're going to overwrite the current standard out of this process, this my.sh process. So what that's going to do is going to take this 0 file descriptor, and instead of pointing to the terminal, it's going to redirect or overwrite that file descriptor with whatever file descriptor we gave it. Overwrite it with the right end of the pipe. Does that make sense? So this is what dupe does. Dupe will take this standard I/O file descriptor,
and it will change this. I'm going to have red. Okay, whatever, green. It'll overwrite that file descriptor with the new file descriptor that we,
And that new file descriptor points to like
the pipe, the right end of the pipe. That's what you'll get from the pipe system call. Yeah. This. Oh yeah, sorry. So I've overloaded the meaning of these arrows. Let me make this a little less overloaded. So forget about those arrows. Those arrows were like inputs to the dupe function. Let me do this in a more kind of semantically coherent way. So let me say green. So this arrow means open file descriptor 0 or standard. Let me just call this standard out. It doesn't matter the number of it. So right now, standard out is pointing to the terminal. When I call dupe, what it does is it redirects, it changes the standard out into whatever file descriptor that we give it. So now standard out is pointing to the pipe, is the pipe open file descriptor. So this is what dupe does. It changes the open file descriptor to be whatever you gave it.
But doesn't replace standard out, it just redirects it.
Well, so what standard out is just the first open file. So standard in and standard IO is just the 0, 1, and 2 file descriptors. So whenever a process is created, the system pre-allocates the first 3 open files of every process. That's the standard. That's what standard IO is. It's just a convention that says whenever you make a process, allocate for me the first 3 open files.
So by default, the standard out would be batch.
By default, it's whatever the parent process was.
Okay, and because batch calls.
Exactly.
Okay.
Because bash calls fork, the process inherits whatever those 3 open files
So
were.
whenever you're running a process using batch, it's making a fork standard.
Exactly. And that's what you're going to be doing in this. You're actually going to be implementing what bash effectively does. You're going to be doing your own fork, going to inherit standard IO, and redirect it. And redirect it is just changing which file the standard IO is pointing at. That's effectively all it is. Yeah.
Would you have to use dupe 2 for this to specify where you want to go?
Yeah. It would be dupe 2. You're right. It would be dupe 2. Okay, so that's redirecting this copy of my.sh to the input of the pipe. Yeah.
If you fork from there, does it also go to the right?
Yes. Yeah. I mean, if I fork from here,
Yeah.
yeah, you just have another copy of my.sh. Its standard out would also be the pipe because all the open file descriptors are duplicated. But good question. Yeah.
So if dupe 2 requires 2 file descriptors, which file descriptor actually resembles the pipe? So like if you have to redirect it to the pipe, right? How does it
Yeah.
know that? How does dupe 2 know that you're redirecting it to?
I'll show that when we get to the code. You call pipe, and pipe will give you file descriptors. And you just save those file descriptors and use those in dupe to overwrite standard out. But I'll show that when I get to the code. All right. So now we've got a new process. Its standard out has been redirected to the pipe. And so now if we want to run LS, so we're not actually running the LS program. We've just set up the process, the kind of metadata of the process. How do we now run LS in this process? Exec. Yeah, exactly. So what exec does is it overwrites the current process's running program with a new one. So this is what exec will do. And I asked you about variations of exec, kind of like a very nitty-gritty detail. I'll give you an example of which one to use for the project. Okay, so now
we've got ls running with its standard out being redirected to the right end of the pipe. All right, so how do we complete this? How do we get, so I said it, but I didn't write it down, but we're trying to implement ls piped to wc. What is wc? Good, yeah. Oh, yeah. Oh, yeah, word count, wc. All right, so how do we do the wc part? Let's have you guys walk through it. Yeah, I think your hand was up first, yeah.
So you can fork my shell again.
Okay, so let's fork my shell again. And so what program is running in this process? My sh. Good. Okay, let me ask someone else. What can we do next?
You would then do 2 for the standard in for the new forks for my shell.
Good. So what's the standard in right now of my shell?
It's whatever it was for the master my shell.
Great. Yeah, exactly. So standard in is now the terminal. Okay, good. So we use dupe2, just like we did before, to redirect. So dupe2 to redirect, in this case, standard in. So the arrow here means like, well, let me maybe make the arrow go this direction. So my arrow semantics are very loose, okay? I don't have like a rigorous semantics of my arrows, but when you use dupe2 here, you're redirecting the standard in to the read end of the pipe. Yeah.
When you first forked the second MySH,
Yeah.
did it still have access to the read end of the pipe?
Yeah, it does. It does. And in fact, so good practice is actually to close that read and write end because you don't need it. Yeah, you could get away with not doing it, but if you read the Linux programming interface book, it's cleaner. You close the end of the pipe you don't need in that process. Yeah.
When you say fork again the program, you're working on the parent directory, or you actually fork the program again?
So remember, programs don't get forked, processes get forked. So this isn't like the text of the program. This is a running program, and that gets forked. Does that make sense? Or are you asking something else?
Is that the split of the previous one, or did you split it?
So okay, that's a good question. So when I did this fork, we had the MySH running program and then the child version of MySH. I forked from the parent, the original from the original parent process. You'll see when I get into the code how this looks. It's more straightforward than you might think. You just check if you're in the parent and then go to fork the other program. But hopefully it'll be clear when we look at the code. But that's a good question. Okay, so we forked MySH again. We've redirected instead the standard in to be the read end of the pipe. So now what's the last step to get this whole pipe set up? Someone different. Go ahead.
Exec WC.
Exactly. We exec the WC program. So exec will overwrite this program to now run WC. So it's a little messy, but now we set up the whole pipe, and because exec just immediately starts running the program, ls will already have started running, most likely, at this point, depending on how the scheduler is working, and already have started populating this buffer. And then the last thing to do, which we'll see in code, is in the parent. So the parent is still running here. So the last thing to do, so you don't strictly have to wait. I think if you don't wait, it'll kill the processes, and so these may not actually finish. But especially in Bash, without giving other information, without giving other stuff on the command line, having background processes and stuff, what Bash does by default is it waits for all of the processes to finish running. It doesn't allow you to enter more commands until all the processes have finished running. And the system call for that is called wait. Wait will just wait for any child process to finish. It'll block. The program won't continue until one of the child processes finishes. Yeah?
Do you wait after you call for?
You wait after you've set up, after you do fork, exec, and pipe for both. And then once all of this is set up, then you call wait. You actually call wait twice. You call wait for all the children that you have.
Wait is a system call. It can have errors. I've given dealing with wait is kind of annoying, so I've given you a little piece of code that'll just kind of carelessly just wait for every process in a loop. Yeah.
Am I correct that wait will just wait till a certain like signal is reached, and sleep just waits till the specific time is reached?
I think that's probably right. I don't know. Well, it's not so I don't think it's a signal, but the kernel will just block. It'll just stop execution of the program until an event happens. So under the hood, it may be implemented with some messaging or signaling. But from the programmer's point of view, it's not asynchronous. It's not an asynchronous signal. Instead, just like reading a file, if you're waiting for the file to be loaded from disk, etc., the rest of your program is not going to execute until that kernel call, that system call returns. So wait works the same way. It's called blocking. It blocks. It waits. The kernel will not let your program continue until that wait function returns, just like any function call. You had a question, right?
Oh yes, if you kill the parent by SH, the children by now the LS and WC will continue running, but the pipe will
No, well, the pipe will still exist. I am very unclear about parent-child like killing processes. You can definitely kill the parent and have processes still run. I think if a parent exits without waiting, it may kill its children. I can't remember. Does anyone know? But you can certainly write like a shell script that invokes processes, kill the parent, and they'll still run. I think these are called like zombie processes or something, where the parent has died and nothing is there to wait for it, and the child. I think it's a little problem with the kernel like cleaning these up, because the parent is supposed to be the one to wait. But I think you can. I'm pretty sure I've done this, where you can have the parent process killed and still have the children run. But I'm really unclear on how the parent-child and the zombie stuff works in the kernel. That's an area where I haven't looked into enough. But in my personal experience, yeah, you can I've had problems where the child process does not die, and I need to kill it. Yeah. Does that answer your question? Yeah.
It just moves the child to
It moves the child to a init? Oh, okay. Thanks. Yeah.
How do they reuse this pipe with future child processes?
Yeah, I mean, you could. Yeah, you could. Yeah, you technically could. But I wouldn't for the program. I would just make fresh ones. It's easier. Yeah.
is the pipe connected to the parent by SH?
I mean, it's just open files. So any process that was forked has access to the pipe, and the parent still has access to the pipe. So if you close a file in one process, but that file's still open in another process, the process can't read or write from it that you closed it in, but the other process can. Because it's not the file itself, it's effectively a pointer to a table that represents state of the open file. So yeah, all of these processes, unless you close the file descriptor, they'll all technically have access to both ends of the pipe.
If children from different processes has access to the file descriptors, wouldn't they be able to pipe into that way?
Yeah, so if multiple processes have the same open file descriptor in the Unix world, they can all write to it. And it's kind of up to the kernel to order that, depending on how the process is scheduled to be run. You can end up with situations where, say, two programs are writing hello world. It may interleave hello world. It might be HHELOO, it might be interleaved. So there's no, what's that? Well, that's where the tools of threading, the critical sections and what do you call it? I mean, managing multiple processes at the same time, like locking, and these techniques for managing synchronization. That's the word. That's where synchronization tools come in for sure. So the kernel does not provide kind of any specific synchronization when you have multiple files. It's arbitrary depending on which process gets scheduled. So there are additional tools. I think there's a couple of classes here. Multiprocessing is its very own specific and difficult area. And doing synchronization, it's a hard thing to do. Unix doesn't provide it for you by default, but you can. There are other tools for doing synchronization. But yeah, other good question. Yeah, it just kind of punts on synchronization of the kernel. It just says, well, anyone can write to it whenever they are the running process. Okay, so that's setting up a pipe. This is effectively what bash does when you set up a pipe. And this also tells you how redirection happens. Instead of redirecting to a pipe, you just redirect to, you open a file, you get a new file descriptor, you use dup2 to redirect the standard out or the standard in to or from that file. So it works the same way, the same system calls. Yeah? The reason is because we wanted to execute a different program. So as soon as we went to call exec on ls, that would blow away the mysh program. So the mysh program is what is calling pipe and dup and exec. But as soon as you call exec on a process, any other code after that exec call does not get executed because the process's program, the memory where the set of instructions is stored, gets overwritten by the new program that you've exec'd. Yeah?
When you call exec, it still keeps, like how we redirected the file descriptor, it still keeps that.
That's exactly right, yeah. So exec doesn't do anything with processes. All it does is replace it's the text segment of its memory where the program text is stored, the binary machine code is stored. So everything else about the process, yeah, it's open file descriptors, its parent process, all that stuff stays the same. You've just kind of swapped out, you've kind of like made an imposter. You've swapped out just the kind of brains of the process, but everything else about the process stays the same. That's why, that's exactly right. That's why the redirection works. And so the standard I/O is more than just, it's the first three open file descriptors. It's a philosophy of writing Unix tools. So when the developers of LS and WC and all these Unix tools wrote them, they wrote them to use standard in and standard out and standard error, specifically because you can do redirection. So if you know that every program is always going to use 0, 1, and 2 for in, out, and error, then that enables this redirection to be possible. And just like on the bash shell, you can always, at least for these standard tools, you can be sure that the information you want is probably going to be in standard out. And then you can pipe it to other processes or save it. All right, so that's piping. Let's look at how to actually implement this pipe. Okay, so let's try using the kind of tortoise method, or what's probably called the stepwise refinement method, which I pointed this out early in the class, but I'll kind of show this in action. Yeah?
Quick question. For
Yeah.
the next page, do we need arguments for the make function?
No. So if you look at the program description, no arguments for the project description. So this is the usage of it. You just call the program, no arguments. There are some tricks with you can actually pipe stuff to mysh because it's just using standard in, but that's kind of, you just follow the directions on doing that. Okay, so let's see if I can quickly show this kind of stepwise refinement, or the method I'm trying to instill in you, trying to get you to use. Before you write any code, you don't have to write like a formal pseudocode algorithm. These algorithms are actually pretty simple. It's just using the tools, the system called tools, that's hard. So let me start with just copying this kind of overall algorithm. So then we want to fork the process for WC, and same thing. Replace WC's standard in this time with the pipe. Run WC with the new standard in, and then wait for both processes. Okay, where should we start? Where should we start implementing? Okay, that's a good place to start. So so create a pipe. How do we figure out how to create a pipe? Where can you look? Yeah. Okay, so assuming you know how to use pipe already, you could go look at my example code. You could look at the man page. So I gave example code for pipe. So look in my notes. You can use that. I wouldn't necessarily cut and paste it. I would look at it. So let me just show what that might look like if you're doing this kind of from almost zero knowledge, at least about the specifics of doing this. So you look in the notes, it's in here, but here you can see, here's the call to pipe. We need an array, and if you don't know what these mean, then look in the man page. But I can, basically just hand copy this code to set up the pipe for myself. So. So I'm just, look in the reference for the includes that you need for all this. Okay, so I've set up a pipe. I've done this first step here of setting up the pipe. All right, so I guess let's, go ahead.
Question.
Yeah.
Instead of exit failure, could you say return exit failure instead?
Actually, yeah, you probably could. I think it would have pretty much the same effect. I don't know if it'd actually be different, but yeah, I think you probably could do that. Okay, so for forking, this is actually the program that I'm writing. So we probably shouldn't look at this. This is too easy. Let me go to process creation. All right, so the next thing we need to do is fork a process for ls. But remember, we're going to do some redirection first before we fork. Okay, so how do we fork? And how do we fork and make sure that we know the difference between the child and the parent process? Yeah, we can use this switch statement or an if statement. So notice it's a single equal sign. That's a gotcha in C programming. So there was an error with fork here. So probably don't need break, but that's okay. Okay, so now in the child process, so before you go, just copying whatever this is doing, keep in mind that this is a different program. It's not going to be doing the same thing that you necessarily want to do, but you can at least take the structure of fork now. So now we've got the system call for the system call set up for fork. Okay, so what do we want to do in the child process at this point?
Change the read input directed to read input.
Right. So I'm going to just copy my pseudocode in here to keep track of it. And in the parent process, what do we need to do? Continue forking and stuff. So I'm gonna, just let this continue past the switch statement. So you could certainly put all your code here in default, but I'm going to use the C style of keeping, the nesting pretty flat. So after this default happens, I'm intentionally going to leave this blank, intentionally left empty. So here, I'm still in the parent process here. But in case 0, I'm in the child. Okay, so what do we want to do first? Should we continue with the parent process or work on the child process? Okay, so let's look at the child process. So there's two things we need to do. We need to redirect standard out, and we need to run with the new program. So let's run the new program first, because I think that's something, hopefully everybody has seen this. So I want to just show here that you don't necessarily have to write this code in a top-down fashion. You can work on different parts. You can do the low-hanging fruit first, and I would say also make sure you test and run this. I'm not going to go through that now because I only have 20 minutes left. But make sure you're testing as you go along. I mean, do sanity checks. Actually, I should do some sanity checks myself. So you can see I already have an error here. So make sure you're testing and running. So I forgot the PID variable. Actually, it's supposed to be, if you look at the code, it's supposed to be this. Okay, so I've made a new PID here. Program compiles. You should also try running it. And yeah.
Is there a good way to get like a separate terminal window and then like a separate editor window, like split up like that?
Absolutely. Use Byobu. So I showed this in, I think, the lecture on editors, which I know I was, hopefully you got that, but use the Byobu tool. And now I can have my program here and F2 to create a new session, so I can compile my program here. And you can switch back and forth.
Is there a way to like take it out though, and like separate them in like two different windows?
Oh, in Byobu, yeah, I think you can do split. Let me see if I remember how to do this. Yeah, there's a way to split in Byobu. I would just Google it for using Byobu. There's a way to split them. But yeah, you can do that. You can do that. Okay, so let me get out of here. Yeah, use Byobu to do it, or you could SSH twice as well. That could be another way to do it. Okay, I don't need that. All right, so I'm going to go through this. So make sure you're compiling and testing as you go along. But I'm just going to, for the sake of time, I'm just going to go through and finish up this coding example. All right, so here I'm going to use, let me actually use this other system call that I encourage you to use for the project. It's called execvp instead of execve, which I showed in prior classes. So what's the difference between execvp and VE? This was homework, right? This was a homework question. Yeah.
Well, for XCVP, if the hashtag exclamation mark is not found and it's not in the beginning of the script file, the XCVP command will actually continue with its work. It will actually ask to the bash terminal or to terminal, and it will interpret the script that makes sense.
So yeah, I mean, the kernel, the loader has built in a capability to run scripts, and so it will. So that is true. I mean, I think you read this right in the Linux programming interface.
Yeah, I didn't really understand it, but
Yeah, so this is having to do with the fact that the kernel can run scripts and execute a script interpreter for you. But that is one behavior that it does. But I guess in terms of like the arguments that are passed and the difference between file and path name, what are the differences? Let's go here. Yeah.
For the P suffix, that allows the program to be specified with only the file name, and then for the V suffix, that gives it the ability to use an array rather than a list.
Yeah, that's right. And so this is super like detailed, but basically what you get is you don't have to specify the full path name of the program. Execvp, the P part will search the path for you. And the E part means you have to specify the environment, otherwise it gets duplicated from the parent. But basically this execvp is, I think, the easiest way for you guys to run a child process. Yeah, go ahead, yeah.
What is the environment for your
What's that again?
Like, what is the environment for your
So I mentioned this briefly when we talked about the the path and the environment. So this is a Unix philosophy thing. There's just a set of variables that are defined for the running process. They include things like the path for lookups, the shell, your home directory. So this is kind of a Unix system thing, this environment. And so that parameter you can use to update or change the environment variables. There are some actually security consequences to the environment, and but yeah, it stores kind of useful things for your interactive system, like your path. Yeah.
Also, like, if I'm understanding correct, execvp will only find something by file name if it's in the path.
Right, if it's in the path in your environment. Yeah, exactly. Exactly. So, all right, so let's try to run execvp. So if you just look at the man page, it says, give a file and give this pointer to an argv list. So let's just let's assume we have it. So this kind of programming style I actually encourage quite a bit. It's kind of backwards programming. So this is the main thing we want to do. We want to call execvp. We might even parameterize this and say this is the prog name. And so this imposes a requirement on you to satisfy these variables. But this is really the main thing you want to run. And so you can just write, nobody's saying you can't write this, something that doesn't build right away. So it's going to break, it's going to complain about this, but the compiler will actually help you. The compiler will keep track of this for you. So this is the main thing I want to run. I want to make sure I do error handling with it. For exec is just run exit afterwards. Error handling as needed, and look at the past lectures on system calls for error handling for exec. But so we got to set up prog name. We got to set up new arg. So notice I'm not even bothering to code here. I'm writing the main meat of what I want to do, which is run exec. And then my compiler is going to, if I don't notice myself, the compiler is going to check for me that I haven't defined these things. So instead of going to coding, I just make a more fine-grained pseudocode for myself. I say, all right, well, this is imposing 2 tasks on me. So instead of trying to do all those tasks from scratch and not documenting it, I actually write comments to say, all right, well, I'm going to have to do these 2 things first. And so that way I won't forget, I won't get lost in all the things I have to do. I've offloaded that work into comments, into documentation. And so this is why, when you hear people say writing comments after code is really hard, or have 2 lines of comments per line of code, what you really want to do is you want to have the comments as pseudocode directing what your program is supposed to do. I mean, there's many philosophies for doing this. But when you're trying to write from scratch, it's useful to use comments and other pseudocode or other organizational tools to keep track of what you need to do, so you're not just coding blind. You're not just trying to code from memory. It's like offloading onto a stack what you need to do, so you don't have to keep everything in memory. All right, so how do we set up the program name? It's a string. So just make a string, right? So we want to run ls. And all right, so then we have this other task for ourselves to do here. New argv. This one's a little more complicated. You just need to make a list of strings, an array of strings. And look at my past code for how to do that. You can also see here how to do it. So I'm just going to make an empty list right now. Okay. So let's see if this program works. So it doesn't like my pointer type, so I made a mistake here. This has to be a pointer to an array, not just a string. And already when I start running this, I'm already getting my ls process running. Yeah?
Why are you doing ls every time? I thought we wanted to do other processes.
Okay, right. So when you write your bash interpreter, you'll have to take in a command from the user, figure out what they're running, and use that. But I recommend doing this stepwise, doing one piece at a time. And so you can use, this is why it's useful to use variables. Because while I'm coding this, I can just hard code something until I'm ready to change this to, user specified string.
We just do scan out?
Yeah, basically. So I have example code for showing you how to do this as well. But do you see the style of coding where you break the problem down into the most fine-grained, like if you're ever thinking, how do I do this? Well, okay, write down steps first. And then if you have to exec a program, then hopefully you know that you need some exec command. So you can freely write exec. You can freely just write it, assuming that the parameters are already defined. And then that, this task is done. So then that imposes more fine-grained tasks on you to define how to define these parameters. So don't try to do it all at once. Break the problem down little by little in this style. And so that way, if you get this right, you don't even have to think about this while you're getting a program name. And you might say here a comment to say, all right, replace with user input later. Yeah. This ends up in the binary of your program. All these string literals end up in a kind of data space in your binary. That's right. Okay, so I've done. This is the kind of stepwise way to do it. Let me show the. Actually, for the sake of time, let me just show the finished program, so that because we only have like 9 minutes left. Okay, but hopefully you get a little sense of this kind of stepwise refinement style of programming where you don't start with code, you start with comments, you start with coarse-grained algorithm, and then take a piece first and break that down. Don't code yet, break it down until you get to a piece that's like a single line of code or a single function or a single variable definition. And there's no rule that says I have to write this before I write the function call. Nobody's forcing you to do that, and the compiler will check for you whether you've done that. So this will hopefully help avoid the thrashing, code a lot, test, something breaks, let me go back and look, code a lot. Instead, I can test this program right now before I move on, which I did. I tested it, I had a little bug. So if you're coding here, if I was continued coding here, and I didn't bother to try to compile and run it, I would have been chasing this bug that I wrote 10 lines before when I was thinking about something else. You're giving yourself cognitive load in programming. And so great programming is not actually about being like super smart and keeping everything in your head. You can't for a substantially large program. It's about breaking the problem down, being organized, compartmentalizing things, using program extractions like functions, comments, or tools like comments to break the program down into easy parts that are easy for yourself. That's the whole spirit of, if you're as clever as you can be when you write the code, how will you ever debug it? So write the code in the more simple-minded way, and then debugging will be a lot easier. All right, let me show the final result here. So some of the variable names are a little different, but here's the pipe, and here's the first fork. So this is the whole first fork here. I used an if statement instead of a switch statement. Here's the child. So the child code is a little bit more involved here. So let me go through it. So there's our exec. I used exec VE in this version, but the algorithm is the same. So there's the exec VE part. Here is what the pipe looks like. So there are a few steps here. One is closing the read end of the pipe, and then calling dupe2 to redirect. And then finally, to make things clean, it'll happen when you close the program, but also closing the end of the pipe that we wrote to. Yeah?
Is a std out file no like standard out?
Standard out, yeah, that's right. So there's really only three main things going on here. Closing the read end of the pipe, which is kind of optional. Your program will still work. Calling dupe2. So that was, if you look in our file here, we've already called fork. This is the dupe2 part. Closing the right end of the pipe, cleaner to do that, and then calling exec. So there's really only like three calls here. Close the read end of the pipe, duplicate the right end of the pipe to standard out, close the right end of the pipe because you're done, and calling exec. So that's why writing the algorithm is so much easier, because you just have those 4 steps. Really 2 steps if you want to be like lazy about closing files. There's really only two steps here, dupe and exec. And getting all the stuff around it right is not so much about doing top-down coding, but it's about writing those first. Even if it's just a comment, writing that first, and then setting up for yourself more fine-grained tasks to do. So once you set up the exec call, well, okay, I need a program name. Let me make that one task. Let me offload that in a task. All right, I need an argument. Let me offload that task. Don't try writing code. Offload it into a comment. Same with dupe. All right, I need to do dupe 2. I need whatever the right end of the pipe is. You can even make a variable name called right end of the pipe. And I need the standard out. You could make those variables. So you wouldn't even have to know ahead of time, a priori, which parameters to write. You could say, okay, I know I need the right end of the pipe, and I know I need the standard out file. And you could write this code, and you've already written the most important part of this part of the code. And then that gives you two other tasks, to set the right end of the pipe and to set the standard out file. So that way you can break these tasks down without having the cognitive load of thinking about the whole holistic program. And so the right end of the pipe, you might say, all right, I know it's in pipe FD. So let me make a new variable here for the right end of the pipe. I know it's pipe FD, but which one is it? And so at this point, because you've offloaded all the other tasks from your mind, you can just focus on this one little task and go out, look in the man page. Okay, the pipe 0 is the read end, so I need pipe 1, the right end. Come back, finish it, try to build it and test it. Well, it's not going to build. It's going to tell you that you have standard out missing, but if you made a mistake here, the compiler will help you a little bit. And then work on the standard out file. So you can just look at my example code for a lot of these parameters. But I could have easily just written it this way instead of getting out this exact code in this exact way. Questions on this? Questions on this style of coding? Yeah. Yeah, you have several weeks from ISH. So my ISH is 10/22. My ISH. I made this out pretty long because I thought it might have some trickiness with this. So take a look at the rest of the notes from today. There's example code for processing the strings. I kind of assume you know some string processing. You can use the string toke function. I've given you the code for doing this, so you can use that for processing the input. All right, everyone. So see you on Thursday. Bye.